In this presentation, we'll discuss Laplace transform and inverse Laplace transform in more detail. We'll clear up some of the mathematical fine points that I alluded to in my last presentation. So what is Laplace transform again? We write x of s is equal to the integral from minus infinity to infinity of x of t e to the minus st dt. And I'm introducing a new notation here, the script L notation. We write script L of x of t is x of s. So the script L is the Laplace transform operator transforming x of t into x of s, and it stands for the integral from minus infinity to infinity of x of t e to the minus st dt. We'll be using that notation throughout the course, so we don't have to write out that integral. Now below we have the inverse Laplace transform. We write x of t is script L inverse of x of s. So there's the inverse Laplace transform notation. And of course, that operator is an integral in the complex plane of 1 over 2 pi j x of s e to the st ds. You note what's happening here. By integrating over s, we integrate it out, and we leave just t. Therefore, it's a change of variables, going from x of s back to x of t, just like the Laplace transform integral integrates out t, leaving s, going from the time domain to the complex frequency domain. Now we have to choose, for the inverse Laplace transform, the appropriate path in the complex plane so that the integral converges. All of this is just review from our previous presentation. As we defined it, Laplace transform takes the integral from minus infinity to infinity in time, so it can be used on both causal and non-causal signals, and on everlasting signals, of course. This is referred to as the bilateral Laplace transform. But there's a problem with this definition, and it is as follows. A single x of s may correspond to more than one x of t. So going backward from the frequency domain to the time domain is not unique, and the only way of making it unique is to specify the region of convergence that was used in the Laplace transform. Here is an example. We have two signals, x1 and x2. x1 is a causal signal, and x2 is anticausal. Yet the Laplace transform of both x1 and x2 is the same, 1 over s plus a. So this indicates the lack of uniqueness. If given the Laplace transform signal 1 over s plus a, we would not know how to uniquely go back to the original signal. Would it be x1 or would it be x2? Only by specifying the region of convergence in addition to the x of s would we be able to uniquely go back to x of t. However, if we restrict our analysis to causal signals and to causal systems, then we do not need to worry about the region of convergence. We'll always have uniqueness. We'll be able to go from x of t to x of s and back again. This is the unilateral Laplace transform, and x of s is given as the integral from 0 minus to infinity of x of t e to the minus st dt. We only integrate from 0 minus to infinity because we don't need to worry about the integral from minus infinity to 0. X of t will be 0 in that segment. We will gain a lot by restricting our analysis to causal signals and causal systems. Most mechanical systems are of this nature, and the signals of interest can generally be treated as such. And by making this restriction, we greatly simplify much of the mathematics of what we will do. So now that we've defined the unilateral Laplace transform, let's actually perform it and determine the Laplace transform of a few signals. We'll start off taking the Laplace transform of Dirac delta function. So the Laplace transform of the Dirac delta function is the integral from 0 minus to infinity of the Dirac delta function times e to the minus st dt. And this will be e to the minus st evaluated at t equals 0 from the sampling property of the impulse. Of course, that's equal to 1. And that's true for all values of s. The region of convergence for this Laplace transform is the entire complex plane. In our second example, we'll determine the Laplace transform of the unit step signal. So the Laplace transform of the unit step is integral from 0 minus to infinity of the unit step times e to the minus st dt. Now the unit step over this range from 0 to infinity is 1. So then we can simplify our integral as the integral from 0 to infinity of e to the minus st dt, which of course is minus 1 over s e to the minus st evaluated at the two endpoints of the integral, 0 and infinity, which will be equal to minus 1 over s times the quantity 0 minus 1. Now, to get e to the minus st evaluated at infinity to be 0, we'll have to assume that s is a positive number. Otherwise, the integral won't converge. But as long as s is any positive number, e to the minus st at t equals infinity will be 0. So we find the Laplace transform of the unit step is equal to 1 over s, and the region of convergence associated with this integral is the right half plane, that is, values of s greater than 0. Hopefully you see that finding the Laplace transform of signals is really not that hard. It's just performing an integration. The inverse Laplace transform is a little bit more tricky, but we could do that as well. But we usually won't. Usually we'll just use a Laplace transform table to find the transforms in the inverse transforms. We may have to do some algebraic manipulations of our signal x of s in the frequency domain to get it ready for the inverse transformation. We'll discuss that topic in another presentation. If you find the Laplace transform table difficult, there still is another option. I recently found this poster which showed that doing Laplace transforms was actually a circus trick. Here you see this remarkable set of pigs that would do Laplace transforms. Incredible. So I have decided that students in MAE 3710 may either use a Laplace transform table or trained animals on any test. I wish you all the best of luck.